Hello, my name is Jeff Messier. I'm a professor in electrical and computer engineering in the Schulich School of Engineering, and this is my video module on the matched filter. Now, to start off this module, I'd like to start off by talking about the digital communications receiver at a high level. When a digitally modulated signal is sent through the channel, it's going to get distorted. Within the channel, there's additive noise processes, there's additive interference processes, and sometimes the response of the channel itself can change the shape of the transmitted signal, smearing it out, for example. That's called signal dispersion. So that, unfortunately, the analog signals that we receive often bear very little resemblance to the analog signals that were generated by the transmitter. And so the job or the task of the receiver is to take these distorted, corrupted, received analog waveforms and try and make the best possible guess as to which waveform the transmitter was actually sending. And this, the whole sort of theory of receiver design is centered around maximizing the likelihood that we make the right choice when we make that guess. There will always be errors, but we want to minimize the probability of an error. And so the receiver basically does this, makes its best guess in sort of two steps. The first step is called demodulation. The second step is called detection. Now, the purpose of the demodulator is to take the analog waveform and basically sample it and extract sort of the key parameters from that analog waveform that will allow us to make the best possible guess as to which waveform was sent. Now, I want to be very clear, this is not the same as Nyquist sampling. So the purpose of Nyquist rate sampling with an analog to digital converter is to create a digital copy of an analog signal that faithfully represents that entire analog signal. The type of sampling we do in the demodulator in a digital receiver is very different. We basically only sample once for the entire received information symbol. For the entire received analog waveform. And so we take that entire analog waveform and we sort of summarize it with just a single sample of information, sometimes of a single value, sometimes a vector of values. And so we're not Nyquist sampling, but we are sampling in such a way that we extract just those parameters that are important for determining the information that was sent, and then those samples are sent to the second stage, which is called the detector. And the detector takes the information from the demodulator, the sampled information from the demodulator, and makes the best possible guess as to what information the transmitter was trying to send. As we're going to see, this sampled information that goes from the demodulator to the detector is basically a signal vector on the same basis function space as the transmitter used to generate the signal, except that the signal vector value isn't going to be an exact match for any of the transmitted signal vectors because of the distortion due to noise and interference. And so this matched filter section is basically a look at the demodulator. So the purpose of the matched filter is to take the analog waveform and sample it, extract the information that the detector needs to make its decision. And while doing that sampling or that extraction, doing it in such a way as to maximize the quality of the information that we're passing on to the detector. So essentially, as you'll see, what the match filter does is basically takes the received analog waveform, converts it back into a signal vector, and ensures that the quality of that signal vector, as measured by something called signal-to-noise ratio, which I'll explain in a couple of slides, ensures that the signal-to-noise ratio for that signal vector is maximized. So we have the cleanest possible information to make our decision in the detector. Okay, we're going to start our discussion off with this very sort of basic high-level block diagram of the demodulator. And so we're going to assume for starters that the demodulator consists of a filter with some continuous time response h, and then a sampler that samples once every symbol interval. And like we were saying, this is not a Nyquist sampler. It samples once every symbol interval, and the contents of this sample should be contain the necessary information for the detector to make its decision on which bits were being transmitted. Now, one thing I should mention is that this continuous time notation is a little bit old-fashioned. So if you read, for example, classic textbooks like Proacus, and indeed really many research papers published even today, we will use a continuous time notation to refer to this this demodulator filter. But really, if we look at the actual implementation of digital communication systems today, this filter would be a discrete time filter. And so we would have at the front end to our demodulator an analog to digital converter that would be sampling at the Nyquist rate, and then those samples would feed into our discrete time filter H. And then this sampler at the output, rather than being a true sampler, would basically be a decimator. But if we were to use discrete time notation, nothing would really change. And in fact, the continuous time notation is a little bit easier to work with. And so for this course, we will be assuming continuous time notation for our demodulator filters. And as I said, this is pretty consistent with the bulk of the research literature that's out there even today. So to start out with, we will assume that our receive signal R that is at the input to our discrete time filter, our receive signal R is equal to two signal components, a desired signal component S and a noise component N. And for now, for this initial discussion, we're going to assume that the desired signal S is deterministic. It's not random. And we'll carry that through the first part of the derivation, and then we'll show how this is extended to random signals a little bit later on. Regarding the noise is assumed to be zero mean, white, and has a passband power spectral density that looks like this. And so on the y-axis, so we assume that the noise is flat over the symbol bandwidth W, and has a y-axis value of 1/2 n naught, which can be considered the energy of the signal. 1/2 n naught is considered the energy of the noise. If you integrate under a power spectral density, the area under a power spectral density gives you the power. So power is of course in watts. And so often the y-axis of a power spectral density we express in terms of watts per hertz, which of course is just equivalent to joules. And the reason why we get the 1/2 here is because we're showing the passband power spectral density. We know from the signal representation module that the baseband equivalent has twice the energy, and so the power spectral density of the baseband equivalent would be flat also, and would have an energy of n naught. So to start with our discussion, the first thing we do is we calculate the output of that demodulator filter with the response h of t, and the output is just the straightforward convolution integral. The next step is to determine the value of the output of our sampler, right? And so that's just the analog output of that signal sampled at time t is equal to capital T. So we just substitute capital T in for little t into our convolution integral. Then the next step is to plug in S plus N in place of the receive signal R, and separate out the convolution integral into two terms. This term represents the desired signal component and is denoted ys of t. This term denotes the noise component at the output of the sampler and is denoted yn of t. And we're going to treat these two signal components separately. So the next step is to determine the power of the noise component at the output of the sampler. So that's just the expected value of yn squared. What we do is we substitute in the convolution expression for yn squared. So that's just yn of t multiplied by yn of t, another expression for yn of t. So there's two because if we're squaring. You'll notice the variable of integration is different in those two expressions just because they're two different equations. On the next line, we group terms a little bit, and you'll notice that this equation contains some components that are random, so the noise samples n are random, but the filter response h is deterministic, it's not random. And so when you take the expected value of a large equation that contains both deterministic and random components, you can kind of zoom the expected value operator in on the random parts, right? So we take the expected value of the noise at time tau multiplied by the noise at time alpha. This is just the autocorrelation expression for the noise. And because we assume that it's white, the autocorrelation is a delta function with n naught as our power for the baseband equivalent signal. And because we've got a delta function in here, a double integral with a delta function basically gets rid of one of the integrations, and we end up with our noise power multiplied by the integral of the square of our demodulator filter. At the introduction to this module, I mentioned that the demodulator, when it samples or extracts the information from the received analog signal, wants to do it in such a way that the quality of the information that it passes on to the detector is maximized. And the way that we measure the quality of the information is with a quantity called signal-to-noise ratio, or SNR. And signal-to-noise ratio is just simply the desired signal power over the noise power. And so the noise power is the expression that we determined in the previous slide. The signal power, the desired signal power, is just the desired signal component squared. And there's no expected value there because for now we're assuming that the desired signal is deterministic. And so from our previous expressions, the denominator here is what we found on the previous slide. The numerator is just the square of the integral expression for the desired signal component ys of t that we found 2 slides ago. And so this is our signal to noise ratio. So at this point in the derivation, what we want to try and figure out is what does the filter response h need to be in order to maximize this signal to noise ratio, right? Because we're focusing very specifically on demodulator design. H is one of the design parameters under our control. And given that we know S, given that we know our noise power, how do we construct H in order to maximize our signal to noise ratio? The way we perform this maximization is using something called the Cauchy Schwarz inequality. And the Cauchy Schwarz inequality just says that if you've got the integral of 2 waveforms multiplied together squared, that's less than or equal to the integral of the square of the first waveform multiplied by the integral of the square of the second waveform. And the nice thing about the Cauchy Schwarz inequality is that it gives us the condition to achieve this upper bound, right? So I mean the right-hand side of this equation can be considered an upper bound because the left-hand side is less than or equal to it. We achieve this upper bound when G1 and G2 are equal to within a constant. And so this allows us to define an upper bound for signal to noise ratio. So the numerator of the signal to noise ratio has the same form as the left-hand side of the Cauchy Schwarz inequality. And so if we keep the denominator unchanged, signal to noise ratio is less than or equal to the square of the integral of the square of the signal multiplied by the integral of the square of the filter. And we achieve this maximum when the filter is equal to the signal within a slight modification, basically a flipped and shifted version of the signal. You'll notice also that when we separate this out, we can cancel those two terms on the numerator and the denominator, and we have the upper bound on our signal to noise ratio is just being equal to the integral of the square of our desired signal, which is just our signal energy, divided by n naught. So in the previous slide, we saw that we achieved maximum signal to noise ratio not exactly when the filter response was equal to the signal. So we didn't have h of t equal to s of t. We didn't have that. Instead, we had h of t is equal to s of t minus t. So what does this mean? It's basically a flipped and shifted version of the desired signal. So if this is s of t, let's say just for this example, it's this sort of half triangle. When we take s of minus t, all that does is flip the signal around the y-axis, take its mirror image. And then when we add t to the argument, we just delay the signal, we move the signal to the right by t. And so it's a flipped and shifted version of the desired signal. So what we went through in the previous slides was basically, a very quick summary of the standard matched filter derivation that you can find in most undergraduate textbooks. And the reason why it's called the matched filter is because, as we saw, the response of the demodulator filter is basically matched to the shape of the desired signal. What some books often don't do is discuss how this simple derivation with the deterministic signal kind of matches or maps into more sophisticated modulation schemes where we have random signal components. So clearly communication signals transmit multiple signals at random. And so what happens, for example, when we have PAM, right, where we have a bunch of different signals that have different amplitudes, but a common pulse shape? Basically, what we do here is we match the filter to the pulse shape g of t. And so this raises a couple of questions. First of all, does it still maximize signal to noise ratio? And the Cauchy Schwarz inequality says that it does, right? So the two signals in the Cauchy Schwarz inequality don't have to have exact equality, they just have to be equal to within a constant, right? And so if we change the amplitude of our desired signal and we still match the pulse shape, then we still maximize signal to noise ratio. And this is also nice because often the communications channel will attenuate the signal by some amount, and it's not necessary for us to estimate that amount exactly in order for the basic matched filter to work. What about the fact that the amplitude is random and changing? Well, basically, we can think of the matched filter as operating over one symbol interval at a time, right? And so within one symbol interval, the amplitude will be unknown and random for the signal, but it doesn't change the fact that signal to noise ratio is still maximized because the amplitude is constant within the symbol interval over which the matched filter is operating. So that's fine for PAM, but now what happens when we actually change the fundamental shape of our waveform? And this occurs certainly with orthogonal modulation when we transmit different waveforms, but also even with PSK or QAM, right? Because as we change the phase of the cosine wave, you can think of it as changing sort of, or at least shifting the shape around of the desired signal. And so the way that we handle this is rather than having a single matched filter, we have a bank of matched filters that are matched to the basis functions of the transmitted signal. So first of all, a couple of questions here. Does this still maximize signal to noise ratio? Well, it does for each basis function, because we know from the basis function equation, or from the signal vector equation, that the transmitted signal, and for this particular case I'm neglecting the noise here for a moment, for the transmitted signal we have our basis function f1 multiplied by the signal vector value, which is some amplitude. And so when we feed this signal into a matched filter that is matched to the first basis function, it doesn't matter that the basis function is scaled by the signal vector value in the received signal, because as long as our signals are equal to within a constant, then we still maximize signal to noise ratio. So you can show that you maximize signal to noise ratio for each of the signal vector values, and because those signal vector values span or define the received signal across the basis function space, then we basically maximize signal to noise ratio for the overall signal. And so this still maximizes signal to noise ratio. But as I've drawn this diagram, you'll notice that basically R of t is split and is fed into both of these branches. And so it's not just SM1 times F1 that's going into the upper branch. The second basis function is going into the upper branch as well. And you might look at that and say, well, geez, does this cause interference or some kind of performance degradation? Luckily, it doesn't, thanks to the nature of the orthonormal nature of the basis function set. I'll demonstrate that in the next slide. Also, at the output of our sampler, we will show that in the absence of noise, the output of the first demodulator bank matched to the first basis function and sampled will be equal to the first signal vector value, and the output of the second demodulator branch matched to the second basis function and sampled will be equal to the second signal vector value. And so this demodulator, when you match it to the basis functions, you can think of as kind of a signal to signal vector converter. Okay, to finish up this module, I want to just illustrate a couple of things about, or clarify a couple of points that I made on the previous slide through a simple example. So I said, first of all, that, for example, the upper branch of our demodulator matched to the first basis function was going to recover the first signal vector value. And I said, second, that the signal component corresponding to the second basis function that also goes into that upper demodulator branch wasn't going to cause us any problems. And so I want to just do a quick example here to illustrate how that works. And so what I've got here is the equation for the output of the top demodulator branch in the previous slide, the one matched to F1. And so our received signal, again, is just S of t. So we were assuming no noise here just to make things a little bit simpler. And we're matched to F1 of t, the first basis function signal. If you look at our argument here, these two capital T's cancel, the negative turns to a positive on the tau, and so what we end up with is the correlation of the received signal with the first basis function signal. I then put in the equation, the signal vector equation for S of t, and then separate out the integrals. And so we have the first integral here corresponding to the signal component, or the desired signal component consisting of the first basis function, and this is the integral for the desired signal component corresponding to the second basis function. Now, this is where the orthonormal property of the basis function signal set really comes in handy. So take a look at this first integral here. We have f1 of t multiplied by itself. The integral of f1 of t squared is always equal to 1, right? Because we've normalized our basis function signals to have unit energy. Over here, we have the integral of f1 of t multiplied by f2 of t. All the signals in our basis function set are guaranteed to be orthogonal. And so this integral goes to 0, and the result is the output of the demodulator is just equal to the first signal vector. And you can do this exact same thing for the bottom demodulator branch and show that the output of the bottom demodulator branch is the second signal vector value. And so, just to summarize, thanks to the fact that our basis function signals are orthonormal, we get our signal vector values at the output of the different demodulator branches matched to the different basis function signals. And so, to close this section of the class off, we can think of the demodulator, when we match to our basis function signals, we can think of the demodulator as a analog signal to signal vector converter that maximizes overall signal to noise ratio. And this, the example that I did on this particular slide, assumed no noise. What happens if we would have had noise in this example? Then rather than getting just our signal vector value, we would have some kind of noise term at the output as well. And so the signal vector that we recover isn't going to exactly correspond to any of our transmitted signal vectors because of the noise corruption on each of our signal vector values. And then our discussion of the detector will deal with how we deal with this residual noise in our signal vector values in such a way that we can make the most reliable bit decision possible. So now that we're approaching the end of this module, it's worthwhile talking a little bit more about signal to noise ratio and the different ways it's sometimes expressed, particularly in research papers. So in many, if not most, research papers, one of the most common metrics for evaluating the performance of a digital communication system is to determine the probability of bit error or bit error rate, and to plot it versus signal to noise ratio. And determining probability of bit error is something that we're going to be doing later on in this course in a different module. But if you look at these papers, if you look at the x-axis, the signal to noise ratio axis, you'll often see it expressed not as SNR, the acronym, or as a power ratio, but as EB over N naught, which for short is sometimes referred to as EBNO. And this is an energy ratio, not a power ratio, like we introduced in this module. And it's worthwhile talking a little bit about how what we've dealt with in this module maps to EB over N naught. And so first, a few words about the numerator, EB. First of all, you'll notice that this is the average energy per bit. Now, in theory, we could define signal to noise ratio either using average energy per bit or average energy per symbol. But the industry standard really is to express signal to noise ratio in terms of the average energy per bit, because we want to know how much energy needs to be invested to reliably transmit each individual bit of information. So for example, and comparing different modulation schemes in different systems becomes difficult if you're using energy per symbol. So for example, let's say you have a system that requires a really high signal to noise ratio, or a really high average energy per symbol to transmit information reliably, and you could look at that and say, oh, well, that's not a very attractive system. However, that system might be using a modulation scheme with a lot of symbols in it, so that there's a large number of bits transmitted per symbol. So that's why we standardize on EB. Also, another thing to emphasize is this is average, always average energy per bit. And we know that different modulation schemes, QAM is a good example, different modulation schemes have different symbols with different energies. And so we determine, basically EB is calculated by determining the average energy per symbol and then dividing the average energy per symbol by the number of symbols per bit. Regarding the denominator of the EBNO expression, we know from the start of the discussion in this module that N0 is just the energy of the additive noise corrupting our received signal, and has units sometimes has units of watts per hertz, which is just equivalent to joules. Now, clearly we've got energy per bit divided by the energy of the noise. This is an energy ratio, and we originally defined signal to noise ratio in terms of a power ratio. And so how does this end up working? Well, it turns out that if we work at the output of the matched filter, our power ratio, signal to noise ratio, is exactly equivalent to the energy ratio EB over N0. How does this work? Well, just to recap some of the expressions that we've already looked at, we calculated noise power as the average value of the noise component squared, which ended up being equal to N0 multiplied by the squared integral of the matched filter response. However, if we are using matched filters matched to the basis functions of our signal, then of course this is a unit energy. This term goes to 1, and our noise power is just equal to the noise energy, N0. In general, power and energy are not equal, but this is because we're working at the output of the matched filter. Now let's take a look at signal power. Signal power we defined, again when we were assuming the signal was deterministic, as the square of the desired signal component, which is just equal to the convolution of the received signal with the basis function of our matched filter. Manipulating this, we have our signal coefficient, or our signal vector coefficient, squared out front, the squared integral of our basis function, again, which is just equal to 1. And so our desired signal power is equal to the square of our signal vector component, which is equal to the energy of the component of the signal that corresponds to this particular signal vector. That is, again, thanks to the fact that we're working at the output of a matched filter that is basically convolving our received signal with our basis functions. And so to sum up, the power ratio that we worked with at the start of this module is equivalent to the EB over N0 energy ratio, but only because of these properties of the matched filter and working at the output of the matched filter. The final thing I want to say in this module is regarding how digital communication systems are typically implemented in simulation. So if you are a graduate student working in physical layer digital communications, or if you're working at a company designing these systems from a system perspective, it's a very common exercise to put together a simulation for your particular design to determine most commonly the reliability of the system or the bit error rate of the system. And this is often done in MATLAB, but not exclusively. Many people still program in more basic languages like C or C++ if they need their simulations to run a little bit faster. And there's also open source equivalent versions of MATLAB, packages like Octave. And so regardless of what particular language you're using, most people use a very common most people use the same approach to implementing their physical layer communications. And so first of all, typically people simulate their physical layer systems at the symbol level, at the matched filter output. So unless you are specifically looking at some spectral characteristic of the signal, or unless the spectral characteristics of the signal are really, really important to you, most people don't bother simulating the pulse shape at all. So we typically simulate at one sample per symbol, which is basically at the signal vector level. So you can think of us as sort of taking out the analog channel and simulating it from a transmitted signal vector perspective to a received signal vector at the output of the matched filter. And so these simulations, typically these signal vectors are implemented in MATLAB or whatever language you're using as complex numbers, because we've seen that for the most common types of modulation schemes, QAM and PSK, the desired symbol is typically represented as a complex number, right? So where we've got the two basis functions f1 and f2, the signal vector for f1 is the real component, the signal vector for f2 is the imaginary component, which of course ties back to the whole concept of the complex envelope of a passband signal. And so typically we've got one sample per symbol, each sample being represented as a complex number in the simulation, so that our received signal sample R is just equal to some channel attenuation G multiplied by SM, which is our complex signal vector, plus some complex noise N. And so I mentioned in the previous slide that one common objective for physical layer simulations is to simulate the system reliability, or the bit error rate, over a range of signal to noise ratio values. And so the reason why we do that is because most physical layer systems designers won't know exactly what signal to noise ratio we're operating at, because signal to noise ratio will change depending on the attenuation of the channel, how far your wireless system is transmitting, or how long your cable happens to be. And so rather than trying to anticipate signal to noise ratio, we usually simulate over a range of signal to noise ratio values. And so most physical layer communications simulations will have some kind of a for loop that will determine bit error rate for a range of signal to noise ratio values. And so the way that we typically vary signal to noise ratio in a simulation is that we, first of all, normalize our average energy per bit EB to be equal to 1, to be equal to unity. And so EB is just equal to the average energy per symbol divided by the number of bits per symbol, which of course, in the case of the complex signals that we typically assume, is just the average of the sum of squares of our two signal components, and we set that to be equal to unity, to be equal to 1. Why do we set the average energy per bit equal to 1? Well, in a real communication system, the received signal levels are usually extremely, extremely small. So it's not unusual in a wireless simulation to have received signal powers on the order of picowatts, and across a 50 ohm resistor that translates into voltage levels on the order of microvolts, so extremely weak signals. And so rather than representing these very, very small numbers in our simulation, we just set the average energy per bit equal to 1. And then we change our signal to noise ratio, typically by adjusting the variance of the noise. Right, so we keep our signal power constant, and then we adjust the variance of our noise. And so the variance of the noise, sigma squared n, is equal to the average of the square of the noise component, yn of t squared, which we have shown is equal to n naught. Now, if our signal to noise ratio is equal to EB over n naught, and we've set EB equal to 1, then the variance of the noise in your simulation, sigma n squared, is basically just equal to 1 over your desired signal to noise ratio value. And so that's how you adjust the variance. And of course the noise is zero mean. If n is a complex noise value, then the variance of the real and imaginary components should be 1/2 sigma n squared. So the total power of the noise is equal to 1 over the signal to noise ratio, and you divide that equally across the real and imaginary components of the noise.